So now that we've looked at the main ways atomic spectroscopy is done, let's look at how we actually do this. So we're going to look at how we prepare the samples for this video and the next couple of videos. So the process of atomization, how do we take our sample and turn it into atoms that we can measure with atomic spectroscopy? And we'll also look at the light sources, specifically hollow cathode lamps, which are vital for atomic absorption spectroscopy. So starting with atomization. There's three main ways that atomization can be done. We'll be looking at flame atomization, furnace, and finally inductively coupled plasma, the fanciest one. And talk about what that means. So starting this video, we're going to be looking at flame atomization. So this is the most basic idea here, is that we take some sort of fuel, often acetylene. We take some sort of oxidizer, usually air or oxygen, and we burn our sample. That's the basic idea here. Now, it's not quite as simple as you just throw your sample into a fire, right? I mean, you can do that, but there are ways to we want to make this a reproducible thing, where we get something very similar flame every single time. We don't want a lot of variation, because if our flame differs, that can lead to differences in the signal that we observe. But the idea is that we're gonna take our sample and inject it into a flame where everything burns up. And so to get this really consistent, we use what's called a premix burner. And that's what is depicted in this figure here from your textbook. Basically, we don't want to just like throw our sample in. We want the fuel, the oxidizer, right? And so we can see coming in here is from the side of the fuel and the oxidant. Those are going to come in and mix in together also with our sample. Now, our sample usually is a liquid, and we want to break it up, into small droplets so that they'll burn evenly, right? If we have one big large glob of our sample, you'll burn the outside of it and the inside won't get burned, because it's sort of passing transiently through this flame. So you want to have an even mix of our fuel, oxidant, and sample, and so we use something that's called a nebulizer. Now, our liquid sample comes in here and then hits this glass bead that's right here. And what that does is it takes our droplets that are coming out and breaks them up into a bunch of little droplets, and those will then spread evenly through, mix in with our fuel and our oxidant. These baffles here also help with that, because the samples the larger droplets are going to hit those and break up into smaller droplets. So our sample kind of has to weave its way through here, and then it finally gets injected into the flame, where we have the burner head, and we've lit this up with some way to start the flame in the first place. Then if we look from a side view, if we're looking in this direction, which is where the light will come from our lamp, will come along the flame, one or the other, but along the length of the flame. And the reason we have this flame spread out is that gives us a little bit longer path length, right? The longer the path length we can have, the more signal we'll get in terms of absorption spectroscopy. If we look from the side, we can see there's sort of, right, here's the bottom, this part right here is down here, and here's our flame here. We see sort of different regions in the flame that are different temperatures, and we want to pick the thing that'll optimize our signal from this. Okay, and so this flame, obviously the temperature of it is going to matter and how well our sample atomizes, and depending on what sort of elements you're looking at, you may need hotter or cooler flames. And so we can control that by picking, we can control the temperature with the fuel and oxidant we choose. All right, so if we go down here, I've got a table from your textbook that shows the maximum flame temperatures with different fuel and oxidant mixtures. By far the most common fuel is acetylene. So we can see these three options here. And depending on what we mix with it to make our flame, we can adjust the temperature. So the most common oxidant, the one that we generally use in our inhale, is air. And that gives us a flame temperature of 2400, 2700 Kelvin. If we need to go to a higher temperature, we can use nitrous oxide, N2O, to give us a higher temperature. So 2900 to 3100. It gives us a few hundred more degrees Kelvin, a few more kelvins. And then if we want the best oxidizer we can get is just pure oxygen, which, we are using oxygen with the air, but it's not pure, right? It's just whatever is in regular air. That can lead to an even further increase. Now, you can get to even higher temperatures. You can use hydrogen. But then, of course, this also becomes more dangerous as hydrogen is highly reactive with oxygen, which is the point, which is why we're using it for this. And that can get us up to the sort of almost up to 3000 Kelvin if we want to do that, right? If we look over here. And if we need to get it really hot, we can use this molecule, cyanogen, mix that with oxygen, and that can get you a temperature up to 4800 Kelvin. So, what you need to use, generally the most common is this first one, acetylene with air. But there are, these are other options if you do need to get to higher temperatures.